Hi, my name is Sebastian, and this is a summary of our work on contextual classification with self-supervised auxiliary models. So what do we mean here by contextual classification? Well, we want to improve the performance of a standard deep neural network for image classification by training it on an auxiliary task. Ideally, this task should be somehow related to the original task and should not require additional annotations either. While some semi-supervised tasks like denoising, colorization, or jigsaw puzzles have been shown to help, it is not clear how related, or in other words, how helpful they are with respect to the original classification goal. We asked ourselves why not using the labels from the classification task to define a new auxiliary task. We proposed an additional task that is based on class grouping. Giving a set of labels from the original classification task, we can simply join them and associate a common group label to them. Now, we can let a regular classifier, like ResNet50, train on the data with original labels, while an auxiliary classifier trains on the classification task with the grouped labels. In order to make both tasks converge to a unified representation, we feed intermediate features from the original classifier as input to the auxiliary model. Another way of seeing it is as an auxiliary classifier which attaches somewhere in between the layers of the original model. Since the labels for the task come out of the original task, we refer to this idea as Self-Supervised Auxiliary Learning, or SSAL for short. This setup is known as multitask learning. While the architecture itself has been used in the past, our self-supervised task, based on labels, makes the auxiliary task more directly related to the original task. We study the extent to which this network layout impacts performance. Let's start with how the grouping is done. Starting from the confusion matrix of a pre-trained model, we turn it into a distance matrix such that values closer to 0, but different than 0, correspond to pairs of classes that were confused the most, and therefore we consider them to be the most similar. We then define how many groups we want to have and assign pairs to groups according to our distance metric, such that the resulting number of classes per group remains balanced and mutually exclusive. Don't forget to check our paper for more details. Training the entire network can be done concurrently based on the two available outputs. We calculate the cross entropy of the original label for the main task, and we do the same for the index of the group in which the label has been placed for the auxiliary task. Both terms can be added together, making it possible to use standard methods like minibatch SGD to update the entire set of parameters in a single step. During inference time, we issue a joint prediction by a pointwise multiplication of the main task's output and the output of the corresponding group. Note that this way of predicting is different to the one used for training. We evaluate the accuracy of a ResNet50 model with and without the use of our self-supervised grouping task for CIFAR100 and Imagenet. On both tasks, we report an increase in accuracy of over 1 percentage point. Now, to show that the increase in accuracy is not only due to our proposed model having slightly more parameters, we analyze alternative baselines that also use more parameters. We compare the performance of a ResNet18, a wider version of ResNet18, as well as a deeper and wider version. While the accuracy on all alternatives does increase according to our expectations, our proposed model still outperforms all of them, all while using less parameters. Further experiments using our proposed architecture, but without the group loss or the joint training, showed no significant improvement over the baseline either. An additional advantage of the grouping criterion is that it allows us to gather more information from each individual prediction. With traditional neural networks, we can try to figure out why the network has predicted that this image corresponds to a slide rule, for example by computing its class activation map. However, it is not clear why that particular area is the most salient, or what is the underlying feature that makes this area so relevant. In contrast, our proposed SSAL network offers more ways in which we can gather additional insights. First, we can have a look at the class activation maps of the auxiliary classifier. Here, areas with high activation values can be interpreted as containing features that are common to the original labels within that group. In this example, we can infer that the even black markings or the aligned numbers are the deciding features, as these are likely appearing in pictures of pill bottles, rulers, or remote controls. For a misclassification, on the other hand, we can try to extrapolate why this image of a spatula gets predicted as a pool table. Once more, class activation maps indicate that the upper side is highly salient, although it's not clear why. Once we look at the classes that are grouped with pool table, we find labels where long sticks co-occur with round objects such as maracas, joysticks, or golf balls. In summary, we show how our proposed SAL models provide more explainable and structured predictions thanks to the grouping criterion and training scheme. We conducted a more detailed analysis on the hyperparameter space, showing that they perform not only better, but converge faster than the baseline models. More details in our paper. Thank you very much for your interest, and don't forget to get in touch for further questions or ideas.